There are many equations to use for kinematics in AP Physics 1, but College Board has only given us 3 to use for solving these problems. The first 2 we will use when solving these problems from Quiz 1.2 for displacement, velocity, and acceleration, the quiz you took on AP Classroom. But unfortunately, there's other equations and relationships that you're going to have to memorize. One of those is the displacement relationship, and this actually is just a definition. Displacement is the change in position, so it's the difference between 2 positions. This is your current or your final position. This is your starting or your initial position. And the way College Board does notation for this for AP Physics 1 is the variable with the little 0 next to it, sometimes referred to as x0 or t0 or v0. You could call them x0, t0, or v0. That's the initial or starting condition. And then whatever your final or your most recent or current condition has no subscript next to it. Another equation you're going to need is the equation for average velocity. This was an equation we derived when we did the taking a walk lab, where if you plot position versus time, the slope of this is just the change in the independent variable divided by the dependent variable. In this case, it's x for position and t for time, as opposed to y and x, your normal math coordinates. If you recognize that this is a slope, then maybe you can get away without memorizing this, but you do need to know that this is average velocity. One that we didn't talk about in class previously, and this isn't explicitly mentioned in any of the AP Classroom videos, is average time. These are both average calculations. This one you use if you are using the times or have a time interval available. This is if you just have velocities available. You can either calculate your average velocity from knowing your starting velocity and your final velocity and dividing by 2, or you could solve for one of these if you know the average velocity and know the one of these 2 that isn't there. Average acceleration, we derived this equation from our rolling downhill lab with a bowling ball. If you plot velocity on the y-axis and time on the x-axis, the slope of this is the change in velocity over the change in time. I put on this sheet that the mathematical model for constant acceleration you need to memorize, but that's actually not true. That's written like this on the equation sheet. It's the same exact equation. The velocity is the starting velocity plus the acceleration times time. So these are both written slightly differently, but they're the exact same equation. Problem 1 from this quiz takes a look at an acceleration versus time graph. This is not a graph we've done in any of our labs, but it's the next level up. We did position versus time and then velocity versus time, and we have acceleration versus time. Before I interpret this graph, I'm just going to go through this word problem here and figure out what we're actually trying to solve for. So we have a cart begins to move from rest. Okay. I'm just going to write what I find out as I go. This is a starting condition. So at rest means that we're starting at 0. On a horizontal track, the acceleration of the cart as a function of time is shown on the graph. Which the following correctly indicates the magnitude of the average velocity of the cart during the interval shown and provides a valid explanation. So we need the answer and the correct explanation. So this is acceleration, and we've defined acceleration as a change in velocity over time. And so this is telling us not what our velocity is, but how our velocity is changing over the course of this motion. And we're starting at rest. So at this point in time, our velocity is 0 at the start. And then over the course of the first second, we're going to change our velocity by what looks like 2 meters per second every second, since all these data points are along 2 meters per second. So after 1 second has passed, we're going to go 2 meters per second faster. And so our velocity at 1 second is 2 meters per second. Then here, our acceleration is 0. Okay? But this is not velocity. This is acceleration. This is our change in velocity. This just means that velocity isn't changing. And so we have constant velocity. So we sped up from 0 to 2 meters per second. and now we're just going to cruise at 2 meters per second this whole time while we're not accelerating. A couple ways you can think about this problem. We're looking for what the average velocity is, and we have a velocity, we get to 2 and then we stay at 2 for a while, but leading up to 1 second, we don't reach 2 meters per second until we get to that first second, because our acceleration is changing by 2 meters per second. So we're speeding up here, but we don't get to 2 here. So for this, basically this whole interval here, the velocity is less than 2 meters per second. Okay, so that's going to eliminate a couple of our choices. C and D are gone now because we didn't have an average velocity of 2. We maxed out at 2 and stayed there, but we weren't there the whole time, so it's going to be less than 2. And so looking at our choices here, we can do process of elimination, and also I'll do an explanation as to why B is the correct choice. But A is the explanation is that the cart has a velocity of 2 meters per second for the first half. This is not true. It has a velocity of 2 meters per second only when it gets to 1 second. It never has a velocity of 2 meters per second until it gets that second. It's speeding up, but it was never there. And then it has 0 velocity for the second half. That's also not true. It has 0 acceleration for the second half, so its velocity isn't changing, but that just means that it stops speeding up. It's still going at this velocity. So by process of elimination, we're left with B. But there's 2 ways you can think about it. We have to be, we max out at 2 at the 1 second part, and we're traveling at a speed of less than 2 meters per second during the time interval, so for the first second. We could calculate this as well, and I could figure out, I could use this equation from your equation sheet. This is the model for constant acceleration. And so for that first second, we're at constant acceleration. So velocity equals acceleration times time plus the starting velocity. The acceleration is 2. The time interval, the time is from 0 to 1 second, so that's 1 second. And we started at rest, so we have a velocity of 0. We multiply that, and we get that our velocity is, sorry, this would be 2 meters per second squared. 2 times 1 is 2. Meters per second squared times seconds is going to be meters per second. So that's our velocity right here. We figured this out before. But then we could use this average velocity calculation to get to do the math to confirm our answers. So we know that we start at 0, and we just calculated that by the time we're done accelerating, we have a velocity of 2. And if we do that calculation, we get that our average velocity is less than 0. Or less than 2, I'm sorry. Okay, so velocity, initial velocity times our current velocity. So we get 0 meters per second plus 2 meters per second divided by 2. 0 plus 2 is 2 divided by 2. And so our calculated average velocity is 1 meter per second, which confirms choice B. This second problem is pretty straightforward in that it's just plug the numbers into an equation. Unfortunately, it's not an equation that's on the equation sheets, so you're going to have to memorize this relationship, and it's going to be the average acceleration relationship, and it's explicitly asked for. The acceleration of the car during the 5-second time interval is, and so reading our problem, the car is driving east on a straight level road with a speed of 20 meters per second. So this is our starting velocity. When it begins to accelerate eastward at a constant rate, after 5 seconds, that's going to be our time. And after 5 seconds, the car has a speed of 40 meters per second. So this is our current or our final velocity. So average acceleration is the change in velocity over the time interval. Where delta anything is your current or final condition minus your starting condition or your initial condition. So we have that the car is at 40 meters per second at the end of this interval. We started at 20 meters per second, and this happened over the course of 5 seconds. So 40 minus 20 meters per second is 20 meters per second, divided by 5 seconds, and that's going to give you 4 meters per second, which is the same thing as per second squared. It's going to be choice A. Something that I didn't pay attention to that was a little sloppy on my part, but it works out, is paying attention to directions. But since we're driving east and then we accelerate east, and the car's final speed is final velocity is to the east, everything's going in the same direction. So whatever sign we use, we're going to get the same answer for this. This won't be the case on other problems here, but for this one it worked out. This is going east, east, and east, and we could just assume that this is the positive direction in all three of these scenarios. The third problem uses the average velocity equation again, but rather than solving for acceleration, we're going to solve for the change in velocity as is indicated in the problem. Object on a straight horizontal track has initial positive velocity, undergoes a constant acceleration of negative 5 meters per second squared over the course of 4 seconds. And we're trying to figure out the change in velocity. So we'll use our average acceleration equation. Acceleration equals delta v divided by delta t. The acceleration is the negative 5 meters per second squared. Delta v we're trying to figure out, and delta t was given as 4 seconds. However you move this, get these two together, you can cross multiply, or you can just multiply both sides by 4 seconds. Either way, you're going to get 4 seconds times minus 5 meters per second squared equals delta v. 4 times minus 5 is minus 20. Seconds times meters per second squared. This cancels out one of the seconds in the denominator. So we get negative 20 meters per second, which is choice A. Number 4 requires a couple steps to solve this problem because we're not given all the information we need to make this a really easy problem. We have an athlete sprinting back and forth along a track. Athlete starts at a position of 0. This will be important in a moment. And the athlete's average speed and final position are shown on the table for 5 successive time intervals. Assume the athlete has a constant speed during each interval and quickly changes direction during the transition between intervals. During which transition does the athlete's change in velocity have the greatest magnitude? So the thing that makes this a little bit more tedious is that we're given average speed. Average speed is a scalar where direction doesn't matter, and so this is just how fast the person going. It tells us nothing about the direction. We're going to have to figure out what the direction of the motion is, which will give us the velocity, by looking at what the final position is between each interval. So for this, it says that the athlete starts at 0, and then at A, they're now at a position of 25 meters. So the position increased from 0 to 25. So that means that the runner was going in the positive direction. Then in B, A to B, it goes from 25 to 0. So the runner is going backwards. The athlete reversed direction, so that means that the athlete was going in the negative direction. The athlete then goes from 0 to 75, so that means that they are going in the positive direction. Now they're going forward. Then the athlete goes from 75 to 0, so they've gone backwards, negative direction. And then they've gone, for this last interval, they've gone from 0 to 50, so they're going in the positive direction again. So now we have our velocities. So this has a velocity of plus 5, velocity of minus 4, velocity of plus 6, minus 2, and minus 7. And now we can do our change in velocity calculation for each interval. So for the interval of A to B, delta v is going to be our current or final velocity minus our initial velocity, so we'll always take our second velocity. It's 4, that's the speed, minus 4, that's our velocity, so we're at minus 4 meters per second minus the velocity at A, which is positive 5 meters per second. So minus 4 minus 5 is minus 9. For the next interval, we end at positive 6 meters per second. We started at negative 4 meters per second. So this is minus minus, which will end up being addition. And we get a change in velocity of 10 meters per second. From C to D, we go from minus 2 meters per second. That's what we end with for our velocity. And we started with 6 meters per second. Minus 2 minus 6 is going to be minus 8 meters per second. And then for the last interval, we go from, we end at 7 meters per second. And we started at minus 2 meters per second. So this ends up adding, and we get 9 meters per second. We have to pay attention to the fact that we're looking at the greatest magnitude, which just means which number is bigger if we were to take absolute values of these. Okay, and so in this case, this is 9, 10, 8, and 9. And so the greatest magnitude is going to be between B and C, which is choice B. For problem 5, we're going to have to pay attention to the directions of our velocity and acceleration vectors for this problem. And so let's read the scenario, and then we're going to label everything and declare our positive and negative directions. Two cars pass by each other on a straight road. Car 1 has a speed of v0 to the right. Car 2 has the same speed, but going to the left. Immediately after passing each other, both cars experience a constant acceleration, a0 directed to the left. Okay, so there's a0 and a0. At the instant car 1 comes to a rest, what's the speed v2 of car 2? So the car is going this way, acceleration is in the opposite direction. So when your acceleration and your velocity are in opposite directions, you have to you slow down, or your velocity decreases or gets closer to 0. Here, acceleration is going in the same direction as the velocity, so you're going to speed up. The value of your velocity is going to get larger and larger. There are a couple ways to solve this. I'll show you both of them. The first one is, because these accelerations are equal to each other, you can use them to break down and find out what these velocities are. Acceleration, by definition, and this is a relationship you have to memorize, by definition is the change in velocity over the change in time. And so I could look at the change in velocity for both of these cars. So delta V for car 1 divided by delta T, and delta V for car 2 divided by delta T. It's indicated in the problem that we're looking at the moment when car 1 comes to rest and then figuring out what the speed of car 2 is. So that means that this is happening over the same time interval, which means we can cancel out the time. Now we're going to break this down and look at our current velocity for 1 minus the initial velocity for 1, and do the same thing for 2. Okay? And now here's where we have to declare our directions. I'm going to arbitrarily pick left to be positive and right to be negative. This will work out either way, but the important thing is, because we have velocity and acceleration going in different directions for car 1s, we need to pay attention to our mathematical signs, because this will make the situation work out for us. Okay? Our final or current velocity for car 1, it says that car 1 is coming to rest, so we're ending at 0 meters per second. And our initial velocity was v0, but it's going to the right, so it's going to be negative v0. Our final velocity for car 2, that's what we're trying to figure out. And our starting velocity for car 2 is the same starting velocity as the other car. It said that they're both going at v0, but this is in the positive direction, so that stays positive. Okay. This is 0, so it doesn't matter. Minus v0 is going to give you v. And so to get v2 by itself, we add v0 to both sides, and we get 2v0 equals v2. And so the answer for that matches up with choice C. A similar approach we could use is if we look at each car individually and then set up a system of 2 equations and solve for it. If we look at car 1, and let's try to figure out the value of acceleration. Well, let's set up the equation for constant acceleration. So here's the equation for constant acceleration. Velocity equals starting velocity times acceleration times time. So for car 1, we have final velocity, starting velocity, acceleration times time. The final velocity we know for car 1 is 0. The starting velocity is v0, but it's in the negative direction. And then acceleration's to the right, that was a0. And then t, we don't have anything for that. If I move this v0 to the other side, I end up getting that v0 equals a0t. We could use this to do a substitution for car 2 if we use the same equation. So if we use the equation for constant acceleration for 2, it's going to be v equals v0 plus at. The final velocity we're trying to figure out, the initial velocity was v0, so that stays put, and at is going to be we're going to substitute in, they use a0 for that. So what I could do is I could put this value in, I could do the substitution where this at is equal to v0, and as a result I get v0 plus v0, which ends up being 2v0. It's the same answer. So it's another way to solve the problem. For number 6, I got tripped up when I did this one for the first time because there's some extra information in here that actually is irrelevant to the question. Because we're looking for average acceleration during a time interval. And actually, based on this problem, the time interval actually doesn't even matter. A cart is moving along a straight track and has a velocity of positive 0.5 meters per second. So it's going to be our initial velocity. And a positive acceleration at time 1. So this appears to be our starting time. At time equals 3 seconds, the cart reaches the maximum speed. At time equals 4 seconds, the cart again has a velocity of positive 5 meters per second. Okay, so that's your final or current velocity, but with a negative acceleration. The student claims that the average acceleration of the cart between time 1 second and time 4 seconds is 0. Is the claim correct, and why or why not? This question is a very complicated way of asking what's the average acceleration, and that's a calculation using this relationship. Average acceleration is the change in velocity over the change in time. And so if we use that equation, our final velocity at the end of this time interval, which is 4 seconds, is positive 0.5 meters per second. Our velocity at the beginning of this time interval, which is 1 second, is negative 5 meters per second, and then our time interval is our final time is 4, our initial time is 1, although the time interval actually isn't going to matter here because 0.5 minus 0.5 is going to give us 0, divided by 4 minus 1, which is 3. Doesn't matter what that is because that's going to be 0 meters per second per second. This statement in here is meant to distract you. It has nothing to do with solving this calculation because it's the definition of average acceleration, where it's just final and initial velocities. It doesn't matter what happens in between. If those two velocities are the same, then it has to be 0. And so that's the rationale for choice A. For choice B, we know nothing about the position, and C and D are meant to distract you with that sentence in there about how it reaches its maximum speed. But it's just the definition of average acceleration. Your two velocities, what happens in between, doesn't matter because acceleration is a vector. The key thing you need to know for number 7 is that when you are slowing down, the acceleration has to be in opposite direction of velocity. Okay? If the acceleration goes in the same direction as your velocity, then you're speeding up. And so for this problem, we have 3 carts are free to move left to right on a horizontal track. Each cart experiences a constant acceleration. The initial and final velocities of each cart are indicated on the table. Which cart, if any, has a leftward acceleration? So what we're looking for in all 3 of these scenarios is if the car is traveling to the right, if it's slowing down, it has a leftward acceleration. Or if the car is traveling to the left and it's speeding up, then it has a leftward acceleration. So let's go cart by cart here. We have a cart going to the right at 30 centimeters per second, and now its final velocity is 20 centimeters per second. That means that it's slowed down. And so v and acceleration are opposite. And since the direction of the velocity is to the right, then the acceleration has to be to the left. So this is the correct answer because it's not none of the above, and so it has to be right. But I'm going to go through all 3, the next 2, just to be thorough here. Cart 2, 30 centimeters per second to the left, and then 20 centimeters per second to the left. It is also slowing down, and so the velocity and the acceleration have to be opposite. In this case, the velocity is to the left, and so the acceleration has to be to the right. So it doesn't meet the criteria of the question. Cart 3, we start at 10 centimeters per second to the left, and then we end up going 10 centimeters per second to the right. This is not as straightforward because in order to go from going left and then going back to the right, we have to slow down and then speed up again. But the change in velocity here will give us an indication of the direction of the acceleration. We changed from left to right, and since we end up going right in the end, that means that we ultimately had to be accelerating to the right the whole time. So we're going this way, slowing down, coming to a stop, and then it's going to accelerate this way to the right. The whole time there's a change in velocity to the right. So that just leaves cart 1 was the only one that had a leftward acceleration. Question 8 is going to use this equation from the reference table, although it's in a slightly different form. But if you recognize the definition of displacement, you'll see that we can just move this initial position over. 1.5 kilogram cart starts from rest. Okay, so our initial velocity is going to be 0. Then accelerates at a constant rate of 2 meters per second squared to the right for 5 seconds. We got initial velocity, acceleration, and time. The displacement of the cart over this time interval is most nearly. Displacement is delta x. It's a change in position. This is the definition of displacement, where it's the change between two positions. So we have a final or current position minus our initial position. And so looking at this equation, we can get displacement on the left side of the equal sign if we just move this initial velocity over to here. So x equals initial position plus initial velocity times time plus 1/2 acceleration times time. Okay, I'm going to move that over. So this is displacement. And so now we just substitute our numbers in and solve. Our initial velocity is 0 since we start at rest. That makes our life easier. The time is 5. This actually doesn't matter for this part of the equation because you're just going to multiply it by 0. 1/2 times the acceleration is going to be 1/2 times 2 meters per second squared. And then we're going to do the time squared. When students use this equation, one of the things they forget to do is to square it, so just always keep track of that. And if you do your order of operations, you should do your exponents first and then do everything else. 0 times 5 is 0, that just goes away. 1/2 times 2 meters per second squared times 5 seconds squared is going to give you 25. We square the units as well, so 25 seconds squared. And we have 1/2 times 2, that's 1, and then 25 meters divided by seconds squared times seconds squared. That cancels out, and we're left with 25 meters, which is choice D. This graph for 9 looks very similar to the position time graph we did for when we rolled the bowling ball down the hill. This is a parabolic position time graph, indicates constant acceleration. And so we have this curved graph here. And that might be a little distracting for trying to figure out how to get this answer, because it's going to use an equation that we developed when we were talking about constant velocity. The graph above represents x position versus time for an object being acted on by constant force. The average speed during this interval between 1 and 2 seconds is most nearly. Okay? So here's the interval here at 1 second and at 2 seconds. To get the average speed, or average velocity in this case, speed and velocity are going to be in the same direction, or it's going to be positive in this case because everything's going in the same direction. We're looking for the slope of this interval. Now, this is a curved line, so we can't get the slope of the curved line, but we just want the interval. And so we'll have a line like this. And to calculate the average speed, we're just going to use our average velocity equation from when we did the taking a walk lab, where it's just the slope, it's the change in position over the change in time. So average speed, or average velocity, is going to be delta x divided by delta t. So we'll have our final minus our initial for position and time. So our final position is at 2 seconds, we're at 8 meters. And our final time, at 2 seconds at 8 meters, and then our final time, 1 second, and our initial position is 2 meters. So 8 minus 2 is 6 meters. 2 seconds minus 1 second is 1 second. And so we're left with 6 meters per second, which is choice D. Number 10 is kind of a tricky multi-step word problem. My initial thought when I was looking at this was I thought the answer was no, but if you dig a little deeper, you actually can figure out the answer here, and so the answer will be yes. A person driving the car suddenly applies the brakes. The car takes 4 seconds, that's our time, to come to rest. Okay, that's going to be our final velocity, while traveling 20 meters at a constant acceleration. So 20 meters is going to be our displacement. and we have a constant acceleration. Can the speed of the car immediately before the brakes are applied be determined without first determining the car's acceleration? It seems like if we have a car going this way with some sort of velocity, in order to get it to slow down and come to a stop, we could figure it out if we know the acceleration. We know the acceleration is going in the opposite direction since we're slowing down. But with this information we have, we really can't directly figure out an acceleration. But we're trying to figure out the speed of the car immediately before. So this will be our initial velocity. And we have some information that we can use to figure this out. We're going to have to use a couple equations here. Similar to problem 9, it looks like we're dealing with a constant acceleration problem, so why would we use an equation that we had with constant velocity? But this equation is applicable in this scenario as well, because we can figure out the average velocity from when it was moving to when it came to a stop. It's going to be moving faster than the average velocity at the beginning, and it's going to be moving slower. It's going to have a velocity of 0. But the average velocity can be useful for us, even when we're accelerating at a constant rate, where the velocity is always changing. So we're going to use our equation for average velocity, where it's the change in position over the change in time, or the displacement over time, and we do have both of those values. Delta V, or V bar, average velocity, equals delta x, the displacement, divided by the time. The displacement is 20 meters per second. Or sorry, the displacement is 20 meters. The time is 4 seconds. And so our average velocity as it's slowing down is 5 meters per second. Okay? So at some point, as it was slowing down, it was going faster than this. And at the very end, it was going at 0. It was at rest. But this is as if the car was just, it would cover the same distance as if the car was going 5 meters per second over the course of 5 seconds. We're going to use our other average velocity equation now to figure out what the starting velocity was. And actually, we don't even need numbers for this. I'll do it with numbers, though. Sometimes students have an easier time seeing a problem with numbers than they do with just variables. So the average velocity equation is also the starting and the final velocity divided by 2. We can plug in everything except the starting velocity here. The average velocity we just calculated is 5 meters per second. The starting velocity we don't know. And we know that we're ending at rest, so our final velocity will be 0. And we divide that by 2. So anything plus 0 is anything. And so we have 5 meters per second equals the starting velocity divided by 2. We go ahead and cross multiply or multiply both sides by 2. You end up getting 2 times 5 meters per second. And I could finish the calculation and get 10, but this actually reveals to us the correct choice here. So it seems like we can do it, so our no choices are gone. And yes, dividing the distance by time, that doesn't work. That just gives us the average velocity. It doesn't give us the average acceleration. And so it leaves us with B. Yes, you can figure out the speed of the car immediately before the brakes if you know the average speed and double it. And that's exactly what we did for this calculation here. Here's the average speed, and we doubled it when we consider the average velocity equation. So it's going to be choice B. Number 11 is a straightforward problem here. We're given a velocity time graph similar to the velocity time graph we had from our rolling the bowling ball downhill lab. The average velocity, or the velocity is a function. The velocity of an object as a function of time is shown on the graph. Which of the following is most nearly the average acceleration? That's just an equation. Average acceleration is the change in velocity over the change in time. It's a slope calculation for this line. All 5 points are okay. This would be 4.5, and this would be 7.5. If you want to go exactly on the grid marks, you probably want to stick to any of these 3 points. I'll do the first and the last, but you could do this middle one and the first, or the middle one and the last. You'll get the same answer. Final velocity at 4 seconds is going to be 9 meters per second. And And then the starting velocity, so at 0 seconds we're at 3 meters per second. 9 minus 3 is 6 meters per second. 4 minus 0 is 4 seconds. And so 6 divided by 4 is going to be 1.5 meters per second, which is the same thing as a meter per second squared. So that's going to be choice A.